The lifetime, L hours, of a battery has normal distribution with mean 18 hours and standard deviation 4 hours. Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. Part A wants us to find the probability that a random selected battery will last for longer than 16 hours. So, first of all, if we look back to the start of the question, where we're told that the lifetime has normal distribution with mean 18 hours and standard deviation 4 hours, if we were to write this out kind of in the way we write out normal distribution models, we say that the lifetime has a normal distribution, and then we normally do mu sigma, where mu is the mean, so in this case 18 hours, and then it's sigma squared, and sigma represents standard deviation. So we'd write 4 squared. So this is how we'd write it out, kind of in the format that we write out normal distribution. So now we have this written out. We want to find the probability that a randomly selected battery will last for longer than 16 hours. And since the lifetime is represented with L, we want to find the probability that the lifetime L is greater than 16. The lifetime will last for longer than 16 hours, and that's how we can write that in terms of probability. So if we want to find the probability that L is greater than 16, if we, on our calculator, go to the normal distribution section, and then this is normal CD, because we have an inequality, and we now put in that the lower bound is 16, because the minimum value this can take is 16. And the reason it's not maybe 17, because it's greater than or not greater than or equal to, is because with normal distribution, it's continuous data. We can say that L being greater than 16 and L being greater than or equal to 16, kind of the same thing, and we can calculate them in the same way. So the lower bound is 16, because that's the smallest that the lifetime can be. And then the upper value, the upper bound, we just put as a big number. They say to do minimum 5 standard deviations above the mean, which here would be 5 times 4 is 20, so 20 plus 18. So the minimum that you could set your upper bound here should really be 38, but you can put any number. You could put 50, 100, and it would give you the same answer each time. So if we put the upper bound as 100, just because it's easy. Sigma is 4, because it's the standard deviation here is 4 hours, we've been told this. And then mu is 18 hours, this mean of 18 hours. And if we put this all in to a calculator, to 3 decimal places, or to 3 significant figures, we should get that the probability that L is greater than 16 is 0.691. And that's 3 SF. And now there's one mark available for this question, and it's a mark that comes from getting the answer right. So saying that the probability that L is greater than 16 is 0.691 will get us 1 mark. At the start of her exams, Alice puts 4 new batteries in her calculator. She's used her calculator for 16 hours, but has another 4 hours of exams to sit. Part B asks, find the probability that her calculator will not stop working for Alice's remaining exams. So what this question is essentially asking, if we put it into kind of different terms, is it's asking for the probability that her calculator will last 20 hours, 16 plus 4, given that it's already lasted 16 hours. And it's important that we think of this given that, because in probability, this can be written as the probability that the lifetime of the calculator is greater than 20, it lasts for more than 20 hours, and then we write given that as this kind of straight line, and this does affect the calculation. So given that the lifetime is already lasted 16 hours. And then the other way that this can be written, so what this means, is the probability that the lifetime lasts 20 hours divided by the probability that it's lasted 16 hours. So if we use the normal distribution function on the calculator, when we do normal CD, because this is an inequality. If we set the lower bound as 20, the upper bound as any number that's greater than 5 standard deviations above this, so we could just do 100, and then the standard deviation is 4, and the mean is 18. These are both things we're told in the start of the question. If we do all this, then we find that the probability that L is greater than 20 is if we write everything to 4 decimal places, in the real calculation, obviously use all possible decimal places we're given, but just to write it down. The probability that L is greater than 20 is 0.3085, etc. And we found in part A the probability that L is greater than 16, and we found that to be 0.6915 if we do this again to 4 decimal places. And so if we do this calculation, we find that the probability that L is greater than 20 given that L is greater than 16 is equal to 0.4462, and that's to 4 decimal places. However, this is the probability that one battery will not stop working for this 20 hours, given that it's lasted for 16. But we know that Alice's calculator requires 4 batteries. And so to find the probability that all 4 batteries will not stop working, we need to multiply the probability by itself 4 times, one for each battery. And so the way we can write this is 0.4462 to the power of 4. And this is equal to 0.0396. And that's to 4 decimal places. And therefore this is the probability that the calculator won't stop working for Alice's remaining exams, because this is the probability that each battery won't stop working, not just one battery, all 4. Now this question is worth 5 marks, and the first mark is a method mark for stating this, so stating that we need to find the probability that L is greater than 20, given that L is greater than 16, and then writing it in this kind of division format. And then we get a further answer mark for doing this calculation here, so finding that the probability of L over 20 divided by the probability of L over 16 is equal to this, to 0.4462. And we actually get 2 answer marks for this. One for this kind of ratio of probabilities, and this for the actual answer. And then we get our last 2 marks from this. So one as a method mark for doing 0.4462 to the power of 4, and then a further answer mark for finding that the answer to this question is 0.0396 to 4 decimal places. Alice only has 2 new batteries, so after the first 16 hours of her exams, although her calculator is still working, she randomly selects 2 of the batteries from her calculator and replaces these with the 2 new batteries. Part C wants us to show that the probability that her calculator will not stop working for the remainder of her exams is 0.199 to 3 significant figures. So what this question is telling us is that in the last 4 hours of Alice's exams, her calculator is going to have 2 new batteries in them, and 2 batteries that have already lasted 16 hours. And we want to find the probability that they'll last another 4 hours, given that they've already lasted 16. So if we start off with the 2 new batteries, if they're new, these batteries only need to work for 4 hours to keep the calculator going, which is different to the others, which need to have lasted 20 hours in total. So if these batteries need to last 4 hours each, the probability of that is that the probability of their lifetime being greater than 4, because that's all we need for Alice to finish her exams, that they last more than 4 hours. So if this is for 1 battery, then for 2 batteries, because there are 2 new batteries, if the probability of each is that the lifetime is greater than 4, then we just need to multiply that again for the other battery, which we can also write as it being squared. So this is the 2 new batteries, because they each need to last for longer than 4 hours, L, the lifetime, needs to be more than 4 hours. So if this is for the two new batteries, now what about the two old ones that have already lasted 16 hours? So in part B, we needed to find the probability that the calculator will not stop working for the rest of her exams when all 4 have already lasted for 16 hours. And what there we needed to find was the probability that the lifetime is greater than 20, given that the lifetime is greater than 16, so given that it's already lasted 16 hours. And that found us the probability for one battery that this will happen. And then we needed to do that to the power of 4 to find all 4 batteries. But here we only have 2 batteries that need to do this. So we only need 2 batteries to last for 20 hours, given that they have lasted 16. So if we multiply the probability for the 2 new batteries by the probability that they will last for greater than 20 hours, given that, which we represent with the straight line, given that they've lasted for longer than 16 hours. And then because there are 2 batteries that need to do this, we square it. And this is how we'd find the total probability, because this is for all 4 batteries. This is for the 2 new batteries, and this is for the 2 that have already been in the calculator for 16 hours. So now if we substitute in this with numbers, if we use the normal CD distribution function on our calculator, we find that the probability that the lifetime is greater than 4 is equal to 0.9998, and that's to 4 decimal places. We need to use the whole answer in our calculations, but just for writing down, if we do it to 4 decimal places. And then, as we found in part B, the probability that L is greater than 20, given that L is greater than 16, is equal to 0.4462, again to 4 decimal places, squared. And now if we do this calculation, we find that the total of this is equal to 0.199, and that's to 3 significant figures. And this is the answer that we wanted to find. We wanted to show that it was equal to 0.199, and we've done that because this is the probability for each of the 4 batteries multiplied together. So this question is worth 3 marks, and first of all we get a method mark, and that's for writing out this, so kind of showing what probabilities we need to find and what we're going to then do to them, which in this case is square them all. So this gets us a method mark for just attempting to do this. And then we get an answer mark for finding the probability that L is greater than 4, and then using the probability that L is greater than 20, given that L is greater than 16, which is what we've done in this line here. So finding this value and correctly substituting this value from part B gets us a further answer mark. And then finally we get an answer mark for showing that this probability is therefore equal to 0.199 to 3 significant figures, which is what we were asked to do in the question. After her exams, Alice believed that the lifetime of the batteries was more than 18 hours. She took a random sample of 20 of these batteries and found that their mean lifetime was 19.2 hours. Part D asks, stating your hypotheses clearly and using a 5% level of significance, test Alice's belief. So the first thing we do in hypothesis testing, and as we've been told to do at the start of the question, which is to state our hypotheses clearly. What this means is we need to say what our null hypothesis and our alternative hypothesis is. Now, the null hypothesis, which we write as H0, is that the mean is equal to 18. This is what we were told right up at the start of the question, and this is what Alice is challenging. So the null hypothesis is that this is true. However, the alternative hypothesis, which is what Alice is claiming, is that the mean is greater than 18, because Alice believes that the mean is now 19.2, as this is what she's found with her sample that she took. And therefore, the alternative hypothesis is that this isn't true, and that the mean is actually greater than 18. So we know, as a general kind of equation, we can write, if I put it to the side here, that if x is the random variable, that the sample mean, we write as x with a bar over it, is normally distributed and then we write it as mu, so the mean, comma, and then standard deviation squared, which is also called variance, divided by n, where n is the sample size. So in this case, for example, Alice took a sample of 20, so our n would be 20. But as a general equation, this is how we find how the sample mean x bar is normally distributed. So if we apply this to the context of our question, our random variable is called L, lifetime. So we would write that L bar is normally distributed where mu, the mean, is 18, as we were told at the start of the question. And now here, we know that the standard deviation is 4. So we have 4 squared over n, which is 20. So as this is our sample size that Alice took. So this is how we would write it kind of in this format. And so what we do now is, firstly, it would be worth writing the standard deviation squared over n as a number squared. And the reason for that is for later in calculations. When we use the normal distribution function on a calculator, we have to put in the standard deviation, but this number, kind of the thing after the comma in these brackets, is always standard deviation squared, and it's important not to get that mixed up, because this will change your answer if you just put in whatever this is as the standard deviation. So if we write it a little bit differently, just that L bar is normally distributed with mu equals 18, and then this is just written as 4 over root 20 squared. If we just kind of square root the top and the bottom and take that power to the outside of the brackets, we now have a standard deviation squared. So this is the standard deviation that we would use in our calculator when doing this calculation. So now we want to find the probability that this L bar is greater than 19.2 hours, because this is what Alice found their mean lifetime to be. So we want to see if this sample mean is greater than what Alice said, which was 19.2 hours. And we want to find the probability of that. So if we find the probability that this L bar is greater than 19.2, and then we put this into our calculators using the normal distribution function, we set the lower bound to 19.2, the upper bound to just any number greater than 5 standard deviations above this. So we could just put 100, 1,000, it doesn't really matter as long as it's quite a big number. The standard deviation, and this is the important bit, it is not this whole value, it's just the 4 over root 20, which is about 0.8944, that's to 4 decimal places. And then mu is 18. So if we put that all in, we find that the probability that L bar is greater than 19.2 is equal to 0.0899. And that's to 4 decimal places. And so this is the probability that this sample mean is greater than 19.2 hours. Now, if we compare this to the level of significance we were told to use, we were told to use a 5% level of significance, which as a decimal is 0.05. So if we compare this answer we got to this level of significance, we can say that the probability that L bar is greater than 19.2 is actually greater than 0.05. It's greater than the level of significance. And therefore, we have to say that there is not enough evidence to reject HO, and therefore there's not enough evidence to support Alice's belief, because if there isn't enough to reject HO, and HO is the assumption that the mean is equal to 18, which is not what Alice said, so there's not enough evidence to say that we can accept this alternative hypothesis here. And now this question is worth 5 marks, and firstly we get a mark for stating our hypothesis clearly, as we were told to do in the question. So stating what H0 and H1 are, which we've done over here, gets us our first mark. And now secondly, we get a method mark for writing out this whole equation, or in this form. The mark scheme actually has it just straight in this form, but they mean the exact same thing. So doing this gets us a method mark. And then we get an answer mark for finding the probability that L bar is greater than 19.2 and finding what that's equal to, which is 0.0899 to 4 decimal places. And finally, we get 2 answer marks for these last 2 sentences, because we get one for saying we can't reject H0, so kind of giving a non-contextual answer. So this is just generally looking at the maths, we can't reject H0. And then we get a further answer mark for putting it into the context of the question and saying, well, therefore, there's not enough evidence to support what Alice was saying, and we can't support her belief. And that's last answer mark, so putting it into context. And that's all 5 marks.